today's concept is on relational algebra. So what is this relational algebra and why we should learn this? Relational algebra is actually the theoretical foundation for your relational databases. So when you talk about relational databases, you're storing data in terms of tables, and then you model data as tables, and then you write queries. And what will be the output? When you retrieve data from tables, you also get another table as the output, right? So relational algebra actually acts as a theoretical foundation for modeling data on relational databases, and also it helps us to model the queries on how to retrieve data from the tables. So we are using SQL. We have learned some query language called structured query language. So the theoretical foundation for structured query language, the base for structured query language, or else we can say the mathematical foundation for structured query language itself was derived from relational algebra. So relational algebra is the foundation on which the relational database management systems have been built. And the SQL, the structured query language which you are learning, is actually a commercial version of the relational algebra concepts. So why we should understand relational algebra? Say internally, this SQL, the operations of SQL are nothing but operations of relational algebra. And also to understand the query optimization concepts, we are going to use relational algebra there too. So we should have an in-depth understanding of relational algebra to have this understanding of what this theoretical foundation is all about. Okay, so truly speaking, in a database management systems course, first they should teach you relational algebra, then we have to go to structured query language, because structured query language itself came from this foundation called relational algebra. So we'll see what is this relational algebra, what are the operators in relational algebra. So we have the select operation. So these are the operations, for instance, select, project, union, difference, intersection, join. So we're going to learn these many types of join, Cartesian, natural, inner, outer joins. And with respect to outer join, we have left outer, right outer, and full outer join. Division operation, rename operation, and some aggregate functions. So these are the operations supported by relational algebra. So you would have learned all these things in SQL too. For instance, join may be a familiar term for you. Cartesian, natural, inner, outer join. So the concept as such, how it works is exactly the same. Whatever you have learned here is what is actually proposed in relational algebra too. So this concept of SQL was derived from RA. So when you think about join in terms of SQL, it's going to very well map to what's given in relational algebra. So it's going to be easy for us because we've already seen these things in using SQL queries. We have understood that. So we can very well use these operations, write some queries in relational algebra very easily. It's not going to be a difficult task for us. So let's take all these operations one by one and start applying them in our queries. We'll understand what these operations are. Parallelly, I'll also be posting SQL queries for any relational algebra query so that we can understand the similarities between them. So we'll be able to comprehend relational algebra from SQL too. Just for understanding purposes, I'm going to do that. So let's start with select operation, and for all our queries, so we're going to write some queries in relational algebra. What we are going to do, we're going to write some queries in relational algebra, and all our queries will be based on the tables given here. This is from your textbook. So we'll have the employee table, department locations table, project table, works on table, and dependents table. So employee table has the information of the employees. The foreign key here is department number, and department number is actually referencing what? The department number in the department table. So that's the foreign key. And department locations table. Here location is a multi-valued attribute. So we have a separate table for department locations. The primary key here is a combination of department number and department location. Project, the project table, the primary key is project number. And in the works on table, we have the primary key to be employee SSN and project number. We have a combination here because one employee can work on many projects and one project can have many employees. See, we have taken the same schema that we have used in our entity relationship diagrams here, and this we have already discussed. Just as a refresher, I'm just giving you the definition or the explanation on these schemas. Again, when you talk about employee SSN is a foreign key mapped to SSN of the employee table. Project number is a foreign key that is actually referencing the project number in the project table. When you talk about dependent, we have employee SSN dependent name. This dependent is actually a weak entity, so we are going to have the foreign key as employee SSN here, and the primary key is a combination of employee SSN plus dependent name in the dependent table. So while we are referring to our queries, we are going to use all these tables. We're going to perform some queries using all these tables. Let's go to the operations now. Select operation. What is the use of select operation? It is used for filtering the rows. Normally, how you filter the rows? You use a where class, right? Select star from employee where employee ID is equal to 124. So this is actually used for filtering rows. In relational algebra, the notation is what you're seeing here, the sigma notation. And this is the table name we are going to give. And this is the selection condition that we give in parentheses. Let me put up a SQL query for you so that you understand this. For instance, you take this query. Select star from employee where department number is equal to 4. So this is a filtering condition where we filter the records by rows, right? So here, how you write this query in relational algebra is whenever you have this row filtering clause, what you have to use? You have to use select, that is the sigma. And what is the condition here? Department number should be equal to 4. So you just put that in parenthesis and you write the condition. Department number is equal to 4, close the parenthesis. And on which table we are applying this condition? The employee table. So that is in parenthesis, you have to mention, say if this is employee table, employee. So this is the query in relational algebra. This is in SQL. So this is the equivalent query. And that's what is given here. You put the select operation and then the condition should be mentioned within two angular brackets, whatever condition it is. And the table name in this parenthesis you have to give. So that is how you use the select operation in relational algebra. So I hope you have understood how this mapping works, and we'll take another example. That is this query. Select star from employee where department number is equal to 4 and salary is greater than uh, 3000. So we have two conditions here with an AND operator. So how we are going to do this? So we are filtering rows here, obviously. So what you're going to do, you're going to put a sigma. Whenever you're filtering rows, you put a sigma. And then you put all the conditions here. What are the conditions you're going to have? Its department number is equal to 4. There is an AND condition, and so you can use this symbol. And salary greater than 3000. So what is that? Salary greater than 3000. So we have put the condition on which table you are going to apply this. This is going to be on the employee table. So I'll just write it here. This is employee table. So we have mapped this query, or we have taken this query. We have written the equivalent query in relational algebra. So this is how it looks. And here I'm missing the angular brackets, which you can very well add. So select, the condition is given here. This is the AND operation, and on which table you are applying the condition. So you can have any number of conditions, right? Where department number is equal to 4 and salary is greater than 3000 and employee location should be Vellore, like that. So you can use the AND condition. If it is an OR condition, it's the inverse of that, it's the reverse of that. You can just say, use this notation and you can put up all the conditions. So this is the select operation with conditions on in relational algebra. So when you talk about the properties of select operation, there are some basic properties. Select is commutative. What do you mean by commutative? Say you can very well interchange this. Say I can filter certain rows on this relation using some condition, and on that result I can apply some condition. So here the first I apply condition 2, then I apply condition 1. This is equivalent to applying condition 1 first and then applying condition 2. It's very simple, right? We'll go back to the previous slide and see this. Say, we'll take the same example. Select staff from employee where department number is equal to 4 and salary greater than 3000. So what it means is, first I can filter by salary greater than 3000. I can very well do this, right? I can filter all the employees whose salary, I'll just write salary as salary greater than 3000. On which table? On the employee table. Just give EMP here for employee. Now on this, I can again apply a condition. What is that condition? Select all the employees whose department number is equal to 4. So first I apply this condition, then I apply this condition. What I'm going to get? I'm going to get a result. But if I interchange this condition, say first I take all employees from department number 4 and then filter all the employees with salary greater than 3000, then I may get some other result R dash that will be equivalent to R. So I can very well say R dash will be equivalent to R. So no matter how you apply the conditions, the result is going to be the same with respect to select operation. So that is the meaning here. Select operation is commutative. And you can also cascade. See, based on commutative property, a cascade of select operations may be applied in any order. So there is no order. You can just interchange the operations. First I apply condition 3, next condition 2, next condition 1, or it can be condition 1, condition 3, and condition 2. You change the conditions and you apply that, but then the result is going to be the same finally. Some properties which we may be using in heuristic query optimization and the query optimization algorithm we'll be learning to. That's why we're just having an understanding of all these properties of the select operation. So again, here you can very well either write it like this, right? Select all the employees whose department number is 4, who gets a salary greater than 3000, and then some condition. Or you can put everything as one single condition. This is what we have seen in the previous slide. We use and then we use everything as a single condition. So this result you're going to get will be equivalent to this result. Okay. So let's take some exercises here. Now the question is, select employees with salary greater than 4000 from the employee table. So the employee table we've already seen. The condition here is salary should be greater than 4000. So this is a select operation. So you use this symbol sigma and then you do salary. What is the condition? Salary is greater than 4000. And on which table we are going to perform this? On the employee table. That's it. We have finished one query. Can you take up this query? Select employees with supervisor SSN 112 or 113 from the employee table. Now we are using an OR operator and we have to select only supervisor. SSN should be 112 or 113 from the employee table. How can you write query for this? So it's a select operation. The condition is, I'll just say this is supervisor SSN. SSN should be equivalent to 112. It's an OR operator and supervisor SSN should be equal. I mean, supervisor SSN should be equivalent to 113. It's 112 or 113. On which table? Again, it's the employee table. Very easy, right? Now you take this query, write this query, select employees with department number as 4 and salary less than 2000. So the condition is select. What are the uh, conditions we have here? Department number is 4. Okay, department number is 4 and salary less than 2000. So it is and salary. Okay, and I should not have that. Let me erase that. I didn't mention, I didn't completely write the condition, right? So salary is less than 2000. So that is the condition. Close the parenthesis. On which table? This is on the employee table. So we have achieved the query here. So that's how you use a select operation with the conditions on the tables, and that's how you write a query in relational algebra for that. Okay, so let's move to the next operation, that is project operation. We'll see what is this project operation. This operation selects certain columns from the table and discards other columns. So here we are not talking about filtering rows, we are talking about filtering columns. So we have to see what is this. We call that to be the project operation. Let me give you the notation. So we have this by notation here, and we have to give the column list that we are going to project from a table, and then the table name. It's very simple. Let's take an example. Select SSN name from employee. So from the employee table, I'm selecting these two columns. How will I write that? So this is the project operation. The column names I'm going to give, and then on which table? Employee table. Very simple and straightforward. So project operation is not commutative. You cannot just like that interchange the things. That's project is not commutative like select. So please keep this in mind. Let's take some exercises here. Select department number and salary from the employee table. So here what we are doing here is we are actually projecting department number and salary. So this is like we are filtering columns, not rows. Is there any condition for rows? No. So it obviously means we are going to only project columns. How can you achieve this? You put the project symbol and then you give whatever columns you have to project. Salary. From which table you're going to do? Employee table. Okay. And select birthday SSN from the employee table. This is also very simple. It's just put the column names here. What are the column names? It's birthday and SSN. You just put a command, mention all the column names from which table? Employee table. So we have achieved this. So that's how we use the project operation. Select is for filtering the rows. Project is for displaying only the columns or filtering the columns. I hope you are able to follow this. Let's go forward. Let's take more exercises now. So now it's a combination of project and select. Retrieve SSN and name of all the employees. So we are retrieving the SSN column and name column. So we are taking two columns only from the table. So this is what? This is projection. Whose department number is equal to 5? Here we are filtering the rows. So what condition comes here? Selection. So we have selection as well as projection on this table. So first what we'll do is we'll filter all the employees from department number 5. So for that, what is the condition we have to write? Filter all the employees. Say, let's call this as department number is equal to 5. And on which table you're going to filter? Employee table, right? So on this result, what we are going to do is we're going to project only SSN and name. So after this, I'm going to get all the employees of department number 5. Now I'm going to project only SSN and name. So this will be done on this result. So this is the result. So what we have done here is we have used both the projection and selection together. So that's how you use that. So it can also be interchanged, right? I can first select the SSN and name of all the employees, but can we interchange this? No. Here we cannot interchange this because when I first project SSN and name, I'll be missing out on department number. I'll not be able to filter department number. So we cannot interchange this operations here. Okay, that's what is given here for your understanding. Okay, the next thing that we are going to see is, if it's a very simple query, I can very well write this in one single line. But in case if there are some complex queries, we'll be taking some intermediate results. We'll see what these intermediate results are and how we use that here. Say, selecting all employees from department number 5. So what it means, I just get all employees from department number 5. So we can just consider this to be an intermediate result. I assign that name to be department number 5 employees. So this is one step in the process of achieving a query for this. So let's take some examples. Say I have employee ID 1 is employee ID 111, name is Satish, is from department number 5. Employee ID 112 Ram is from department number 4. 113 Sam is from department number 5. This is the table. First, what I do, I filter all the employees from department number 5. So obviously Ram is going to be left out. So this result I'm going to get, I'm going to give that name as department number 5 employees. So this is the intermediate result I'm getting, department number 5 employees. Okay. So this is what this one. Now what I'm going to do next is I'll take this result, whatever result I have attained. On this, I'm going to project only the SSN and the name. So from this result, just project. So that will be my final result. What is that I'm going to project? I'm going to project 111 Satish and 113 Sam. So from where I have achieved this result? By applying this project condition on this intermediate result. So that's what is the meaning. This intermediate result I'm taking, applying the project condition to arrive at my final result. So here we are taking some intermediate results, just breaking down the query into steps. And for each step, we get a relation, right? Say when I apply this condition, I'm getting this relation out. So this is the name for that relation. And on this relation, intermediate relation, I'm applying the conditions to get my final result. And this operator or this symbol you're using here is called an assignment symbol, assignment notation. So when you have some large queries, you can very well use such notations. I mean, you can use assignment to break it down into simple steps. We can always do that. So next thing, we'll look at the rename operation. We'll move forward. We'll take a look at the rename operation. We all know what is rename operation. You can rename a column name. You can rename the entire table. So you can rename a table or a column, right? So that's what is all about the rename operator here. We call this operator to be a row operator. It's not a P, it's a row. And whatever you're seeing here is, I am renaming this relation R to the new name S. For that, I'll use the row operator, and B1, B2, Bn are the column names. If you want to just discard the column names, what you can do is you can mention it like this. So this is the old name for the table R. I'm renaming it as S, and this is the row operator. Simple example, say I have a table called employee. I am renaming employee to emp. How can I first specify that? Row operator, new name is emp, old name is employee. This one corresponds to all the column names. So if you mention the column names, emp and then all the column names, it means that these are the columns in the new table or the table that has been renamed. Okay, the same example I have given there for your understanding. So now renaming a column alone in a table. I'm not renaming the table. I'm just renaming a column in the table. So here you can see in the employee table, I am renaming name as first name. So how you mention this? You're renaming name to be first name. So you give the new name slash the old name for that particular column. So if I have many columns, you just put a comma and then you specify the new name and then the old name. So here row is the rename operator the new name for the column, the old name, and then the table on which the rename operation for the column happens. So here comes another variation. We are renaming both the table and the attribute. So what we are doing here, row operator. This is the old name for the table. This is the new name. And in this table, I'm renaming the name to be of first name. So I'm renaming name as first name. So here, this query is for renaming both the table as well as the column. So this is the new name for the table and this is the new name for the column which I am renaming. So that's the use of row operator in relational algebra. So what is an union operation? For this, we can consider two tables, say E1 and E2. Let's assume that these two tables have these fields, that is SSN and name. And this also has the same fields, SSN and name. And we can take some records here. Say I have some records of employees 111 Sam, 112 Ram, 113 Pilar Tom. Likewise, here we're going to have 111 say Sam, 112 Ram. When I want to perform a union, what is the symbol I'm going to use? This is the union. So I can perform a union of two columns. That is possible. So how will you write a SQL query for performing union of two columns from these two tables? It's say if I'm performing union of SSN alone. So it's going to be select SSN from which table? Employee one table. The keyword in SQL is union. This union is represented with this notation in relational algebra. So you're going to write select again SSN column from E2. So what will be the output of this union operation? You take all the SSNs from E1 and all the SSNs from E2. So it's going to have 111 SAM. We are not going to have duplicates here. It's going to be 111 SAM, 112 RAM, and 113 Tom. Though we had SAM and RAM here, it was not considered because we are eliminating duplicates with union operator. So that is union. We will now look at this intersection operator. What is this intersection? It is represented as E1 intersection E2. So when I intersect, say I intersect this SSN column with this SSN column. So what does that mean? Whatever SSN that is common in both these tables will be thrown as the output. So what are the SSNs that are common in both these columns? So 111 is present in both the tables. 112 is present in both the tables. So output of intersection of SSN in both these tables will be what? The output will be 111 and 112. So how will you write a SQL query for that? It is nothing but select SSN from E1. The keyword in SQL is intersect, whereas here this is a notation in relational algebra. So we'll do a select SSN from E2. So to perform this operation, the data type of both these SSN should be the same. So only then, you'll be able to perform an union or an intersection. We're talking at the column level here, we can also perform an intersection or a union of an entire table. Then what is the condition? The entire table schema should agree upon. So whatever schema you have with E1 should agree upon with E2. If you're performing at the column level, say this column with this column, then the data type should be the same. Then we have another operator, that is the minus operator. You just say E1 minus E2. See, this is subtracting two tables. If I'm going to subtract the SSN here with the SSN here, what does that mean? Whatever SSN that is here, but that is not here, will alone be considered. So what is E1 minus E2 here? The output will be 113 Tom. That is E1 minus E2. If you consider only the SSN columns, what is SSN here minus SSN here? What will be the output? It will be just 113. So how will you write a SQL query for this? Let me erase certain things here. Okay, let's write a SQL query to find the difference of the two SSN columns. For that, what is the SQL query? It is select SSN from E1. The difference is given as minus, that is the SQL operator, and select SSN from E2. So this, how we can represent this in relational algebra? First, you are selecting SSN from employee 1 minus, we are selecting, we are projecting. What is this? This is projection, right? We are just taking a column. So we are projecting SSN in E2. So this is the equivalent query for this. Likewise, what is this SQL query intersect? What is the equivalent query in relational algebra? You're selecting SSN and then it's an intersect operator. So it is employee 1, we are selecting SSN, intersection SSN column of employee 2 table. So that is the equivalent relational algebra query for this. And for this union, the same thing, except here we are going to have this union symbol. So these are the operations, the union, the intersection, and the difference operations in relational algebra. So two things I have said, you can work at the column level union, or you can perform an entire table level union. When you go in for a table level union, the entire table schema should agree upon for both the tables. When it's a column level, only the column should agree upon. So let me erase all this thing. Let's go to the contents here. So this is what I've told you. This is a column level union, which I'm doing. And you can see that is the corresponding relational algebra query. And we have attained the output. Likewise for difference. So the minus is the keyword in SQL. Whereas in relational algebra, the equivalent query is you project SSN from employee 1 table, project SSN from employee 2 table. So this is the minus operator. Likewise for intersection, the keyword in SQL is intersect, whereas here we are projecting SSN from the employee 1 table, projecting SSN, and then we perform an intersect. If you're just intersecting both these tables just like that without projection, it's employee 1 intersection employee 2. So that's about these operators. The next operator we're going to see is the division operator. We'll understand division operator with an example here. Say I have this table works on and I have this table project. So works on divided by project. So what does that mean is it's going to be the common field. Say project ID is the foreign key here. So when I say works on divided by project, it's nothing but the project ID is common in these two tables. So it's going to take all the project IDs, right? Which employee is working on all the projects? You see 112 is working on all the projects. Whereas 113 is working only on DBMS, 114 is working on DBMS, 115 is working on OS. It's just going to be on the common column name. So when you divide this table by this table, you take all the contents of this common column and you see whichever year, whichever employee has taken up all the projects. So the answer here will be works on divided by project will be 112. If there is another employee, say 115, if 115 has also worked on DBMS, let's assume like this. So here is an employee who has worked on both the projects. So the output also will contain 115. So this is the division operation in relational algebra, and the notation is also given. Okay, so that's the division operation. Let's go to the next operation, the join operation. So we have already discussed join in detail in SQL. That should be of great help to us to understand what is the join operation in relational algebra. So here, when you talk about an equi-join, so whenever you talk about a join, you're going to come with this notation. And this is the join condition. Say when you talk about an equi-join or a non-equi-join, you're going to have some join condition here, right? When the condition is going to have an equal to operator, it's going to be an equi-join. When it's going to have other operators other than the equal to, it's going to be a non-equi-join. So we are going to use this notation, and these are the two table names, and we mentioned the join condition here in relational algebra. So let's take an example. Equi-join employee with department using department number. So we have employee table, department table. Their foreign key in the employee table is department number, and department number is a primary key in the department table. So Which two tables we are going to join? It's going to be employee, and the another table we are going to join is department. Now what we'll do is we'll use the join notation. That is, this is the notation. We have to put relational algebra notation. And then we have to mention the join condition. That is, say department number in the employee table is equal to department number in the department table. So this is how you mention an equi-join in relational algebra. So what is a natural join? You join two tables using the identical column name. So no need to give any conditions in natural join, it does that automatically. So we give an asterisk and then employee table, natural join, department table. So this is the notation in relational algebra for natural join. So if you're not clear with the join concepts, we have already discussed on joins, right? That video is also available. You can very well refer to joins and come here so that you understand what is natural join. Here we are just looking at the notation. We're not discussing what natural join is. Natural join is just joining two tables using the identical column names in both these tables. So we mentioned that using an asterisk here. Partition join or cross join, we use this symbol, into symbol, to say this employee table is having a cross join with the department table. So every row in this employee table will be joined with every row in the department table. That is a cross join, right? So the notation for cross join is this. So what are the joins we are having? Now we have to look at left outer join, right outer join, and full outer join. Say when you're talking about left outer join, the symbol is notation is this in relational algebra. Say for instance, employee, we'll do a left outer join with the department on the condition department number. Then what we have to do is we have to write that as employee, and it's the join symbol. Since it's a left outer join, you just extend it like this. And on which table, department table, we have to mention the condition here. So department number is equal to department number. So this denotes the extended notation like this to the left side denotes the left outer join. If it's a right outer join, now you know what we should do. Right outer join is nothing but the same join symbol with the condition, but it is extended to the right. So this is a right outer join. I also talked to you about a full outer join in my join lecture, right? Wherein we have done left outer join union right outer join. So a full outer join is like this. So you extend it on both these sides. Say if R, the table R is having a full outer join, then you just extend this like this. And then say it's having a full outer join with yes. Okay, so that's about the join conditions and notations for join in relational algebra. As I told you, if you're not familiar with the joins, please visit my lecture on joins, understand that, so that it's very easy. You're just substituting that with a notation here. We also have this aggregate function concept. What is aggregate function? We talked about the max function, min function, average. So these functions will apply on a set of rows and then it is going to give you one single output. So I can find total salary, sum of salary, right? So it finds sum of salary of all the employees and gives me the sum finally. So how aggregate functions are mentioned in relational algebra? For this, we are going to use this script F notation. So this is this notation, and you can see here, I'm finding maximum salary, maximum of salary in the employee table. Then I give the script F notation, the function max on which column I'm going to give the table name. Likewise, I want to find sum of salary of all employees, the script F notation, sum is the function, salary is the column name, employee table. So now there's the next thing we have learned group by, order by, right? Group by. What is group by? I can find sum of salary of all employees based on the department number. Say for department number one, what is the sum of salary? Department number two, what is the total salary like that, right? So here the group by condition is department number. What is the aggregate function? Sum. So how you represent this kind of a query in relational algebra is, I'll just write it here. You just put this scriptf notation, and what is that we are finding? We are finding sum on which column? The salary column. On which table? The employee table. But we are going to have a group by condition here, that is on the department number. So this is actually the query in relational algebra. So whatever group by clause you're going to use, you just put that here. The sum function or the any aggregate function you're going to use on the column, and then the table name. That's about the aggregate functions, and we have looked at all the relational algebra notations. Now we'll take up these two simple exercises before we wind up. So here the query is retrieve the name and address of all employees who work for the department by name research. So here we have the department name, department number, manager SSN, manager start date. So department name exists in the department table, whereas name and address of all the employees exists in the employee table. So if I want to print name and address of employees who belong to the department by name research, what I have to do? I have to join these two tables using the department number. And then I have to project what? I have to just project, say, we just have name column here, name and SSN. Here it is first name, middle name, last name. Let's consider this to be just name and SSN. I have to project these two columns. So what I will do is I can do this in 3 steps. First, I can filter all the departments containing the department name research in the department table. So how will you filter? When you filter rows, you have to use this condition, sigma. And then what is the condition? Department name is equal to research, because we are focused only on this department. On which table? The department table. So this is what all departments by name research. I'll call this D1 or else DR. So all the departments with the department name research is filtered. Next, what I will do is I will join this result with this result. That is, you can perform an equi-join of employee with this result, right? So how can you perform that? It's nothing but employee. We can perform an equi-join. So it is just this condition. And what is the condition? We are going to use department number and department number. So it is department number is equal to department number. It's number here, please. Department number is equal to department number, and we are going to join with the result that we have achieved that contains only all the department names of all the departments that has the name research. So it's going to be DR. So this I can say a result that is coming in as ER. So from this, what I have to project? I have to project only the name and SSN. So the final result will be pi of SSN comma name or name comma SSN on which this intermediate trigger. So this is the output for that. I've got the output here. Let me share that with you. So first, what we are doing here is you can see. First, we are filtering all the departments by name researched on the department table. So that is an intermediate result, right? Next, what I'm doing is this result, I'm performing an equi-join with the employee table using the department number condition. So this will join only employees from department name research with the employee table. That is another intermediate result we have achieved. From this result, I am just projecting the name and address required. So this is going to project the name and address of all employees whose department name is research. So that is the final result we are getting. So there's one more query before we wind up. Retrieve the names of employees who have no dependents. Can you say this is the, let me erase all the ink on this slide and let's go to this. So we have employee SSN and we have the dependents table here. Employee SSN is a foreign key. So this is the primary key SSN here. This is a foreign key in the dependent table. So we track the dependence of an employee, right? Now the question is, find all the employee SSNs. I think find all the employees who do not have a dependent. say only those employees who are not having a dependent should be displayed, and we should also display their entire details. Okay. So how this result has been achieved is it's very simple. I'll show you here. First, I'm projecting all the SSN of all the employees. Say I'll just explain this. If in my employee table, if I have some employees like 11223344 like this, I'm just projecting the SSN of all the employees. And in my dependence table, I'm projecting the SSN of all the employees. So there's a dependent table where ESSN is a foreign key, right? So I'm just projecting this column. Say only few employees have a dependent, say 11, 22, 33. Only these employees have a dependent. So they will be in this dependent column. So when I project this, what will be the output? It will be 11, 22, and 33. Next, what I'm doing is I'm doing a difference. What is the difference? All employee SSN minus employees with dependents SSN. So what is the difference? Whatever that is here but not here alone will be the output. So what will be the output here? The employee SSN 44 will be the output, because that is the difference operation, right? And with this employee SSN, what I have to do? I have to do a natural join with the employee table. So 44 is natural join with the employee table. So I'll be able to fetch what is the record corresponding to 44 in the employee table, and that is the final result. So we are using the difference operator here. Just project SSN of all the employees having dependence SSN, do a difference, and then you do a natural join of that difference with the employee table. You get the details of the employees who are not having dependence. Okay. So I hope you have understood relational algebra. Let me wind up this session.